pen, there's a pen. I'll hope that pen works. Cool. Howdy, folks. Howdy again. Cool, even more people looking at me. Look at that. It's like a guy up here. Crazy. Let's take a minute. So now that we've woken up, can you please stop doing whatever you're doing so we can transition into being together? Let's just take a few breaths together. And a good way to come into this room would be to listen to what's happening in this room. Since I'm late, that's probably good to stop right there. Is there anything I can do for you all? I've heard people talking about homework and stuff. Is there anything you need to talk about? Problems you're having troubles with? Concepts you're having troubles with? Anything that I can help you with before I do my little show today? Let's see how this pen's working. Hi, Lou.
So, like, if the linear equation isn't like already like set, like you have the y1s and then the
Y prime. So Y prime.
Y prime integrating factor, and then this over here, like how do you like take out the integrating factor without like?
I like that question. That's a great question. Let's do an example. So let's say I had a linear equation, and let's talk a little bit more. Thanks for asking, Lou. This is a good thing to chat about. Let's say this equals, do that. So I have a linear equation. Let me say a little bit more about what that means, because it's going to become a very important idea in here, this phrase linear. Clearly line is in there, but mathematically, a line is just the most basic form of linearity. And linearity is actually a much greater property, a much more abstract property that affects or is exhibited by just tons of mathematical objects. It's so important. We have a class in it called linear algebra, where you study just linearity. So what does that mean here? And we can't really get into 100% of what it means, but for us right now, our first order linear equation is going to look like this. And so, Lou, you're right, it might have stuff in front of the y prime at times. Before we can find the integrating factor, so actually, first off, let me just say, this is a linear first order DE. So what I would do is get a 1 in front. For that integrating factor method to work, we definitely need to divide through by this leading coefficient. And then making note of that. So step 1 here would be to do this. And then I can go ahead and find my integrating factor, but I would want to note that I just divided by something that has a variable in it. So whenever x is, where a of x equals 0, that could be a trouble spot for us, and it'd be something we'd want to just note, keep an eye out for, and see if anything weird happens, but just note where, just in case. We're actually going to talk today about situations where a solution doesn't exist, but for today, this will work, just, or at least for the first part of this is perfect. So step 1 is I'm going to divide through by x, and I'm gonna get y prime plus 1 over xy equals x. Let's say we've got an initial condition here, which is probably kind of befouled. So notice that I just divided through by x, and now I've got, this should say y at 0 is 1. X can't be 0 here. So I'm gonna actually modify this to say 1, just to be on the safe side. So that's the kind of stuff I'm talking about, Lou. Things like that might arise. But now I can happily find my integrating factor. It's gonna be the antiderivative of this thing. Put as an exponent on e, so our integrating factor is going to be e to the integral of 1 over x dx. That's going to turn into e to the natural log absolute value of x, and that's going to turn into absolute value of x. We're just going to toss off the absolute values. If you end up with an absolute value at this stage, just get rid of it. So I'm going to convert that into just pure x, noting that already x is at least 1, so you know it's a positive number already, nothing too weird going on. And then I multiply, or I just go ahead and write this left side immediately like that. It's going to be my integrating factor times my dependent variable equals this right-hand side multiplied by my integrating factor, which was just x. So I got an x squared back, which is kind of cool, because I got rid of it, now it's back. This is going to actually look like this. Xy equals x squared. And now I'm going to take the derivative with respect, the integral with respect to x, and that's going to turn into xy equals 1/3 x cubed plus c. And now I'm good to go. Divide through by x squared. So I just wanted to do another example too. Looks like c is going to be 2/3 to make that initial condition work. So long story, very long story, much shorter. Just divide through by that front number, get a 1. Even if that was a 3 out there, divide through by 3. Hey, that's an odd face. I don't know how to interpret that.
So you always wanna, so if it is a y prime, you always want to multiply out the, or divide out the x.
Yeah, or the leading coefficient, the leading x thing. And if this was an x dot, then there could be some t crap here. I would want to get rid of that and divide it through by t. And make sure to do it all the way across. And then you're safe.
And it doesn't matter what the bx is next to?
No.
Okay.
Well, I mean, so the general form here has to be this, otherwise we need a different technique. So if we're solving something that doesn't have the rhythm of derivative plus not derivative with coefficients in front, we should be using a different technique. Do you have a problem in mind that's troubling you? You're just thinking.
Yeah.
Okay, all right, I like that, that's cool. Okay, any other questions?
Nope.
This,
It's good.
you good?
Mm-hmm.
Awesome, solid. We all good? Cool. Let me give you a quick problem and see how it goes. Could you just for a moment, this isn't even a linear equation, this is just a good old separable differential equation. Could you please solve that? And there's a reason we're going to do that. everyone, did you get my reply?
Yeah.
Yeah, thank you though, but Friday nights, like, yeah, got stuff going on with my wife actually. But I really appreciate the invitation. Because I think a lot of you, so that's cool. I'm glad the respect is returned. Just making a little D field to lend to the discussion. Oh, well, that makes sense. What'd you get, Lou?
Yeah, yeah. Where's that?
Because the C's gonna be 0.
Yeah, it's true. I was just curious what that X.
Because you do X over 2 times C, plus things over 2 times C.
Oh. Oh, right. Okay,
Yeah.
you're multiplying it
Yeah,
out. Gotcha.
just-
Gotcha.
yeah, just-
yeah.
Yeah, that's
sorry.
cool. No sorries are needed. That's awesome. It just wasn't what I had in my brain when I worked it through, but it's the same. So, unless you're really good with doing integration, you probably want to get it into this form. So you can do a power rule. And then when you do your power rule, that's going to go to a 1/2. And you're going to divide by 1/2, which is multiply by 2. So I actually end up with that. Let's stop. Let me know. We good? Any questions or troubles? Or did I, if I get it wrong, I'm in one of these moods today. I just came in first class of the day. I could be fucking stuff up left and right. You let me know. I know some of you will let me know. Just don't be gleeful about it. That's all I ask. So I could go ahead and solve for y here, and I think I will. I'm going to divide both sides by 2. So I get y to the 1/2 equals 1/2 x, and absorb that into the c, and then go ahead and square both sides. And so that we get y equals 1/2 x plus c quantity squared. If I look at my initial condition now, c has to be 0. So since y, when x equals 0 is 0, the solution is this. And so you simplify it out, and you get 1/4 x squared, actually, if you just distribute the square. Does this sound good? Are there any other solutions? So we just solved this using our technique, and it looks like this. So here's my initial condition, here's the D field. Since we have square root of y can't be negative, so there's nothing down here. This is the beginning of all solutions. And that solution looks like this. Is there one that we could have? Can you just think, like, just say you come into DiffEQ, you don't know any techniques. What could you maybe guess? And this is hard, so I don't know if this is guessable. I've just seen this example too many times to come at it freshly. Is there a constant solution that might work? Is there an equilibrium solution here? Yeah, so there's definitely this equilibrium, right, at y equals 0. Notice that if I just say y is identically 0, just this function right here, that works. Because the derivative of 0 is 0. And so this says that y prime is equal to the square root of y everywhere, and it satisfies the initial condition. So we have 2 solutions that come out of here. That's disturbing, maybe. How do I know which one's the right one? Which one would if this was a physical system being modeled, which of these two branches would we follow? And the answer is, it's unknown. There is a problem here. Not every differential equation has a unique solution, even with, especially with initial conditions. So let me just kind of state what the summary of that is. So it's clear that not every first order initial value problem has a unique solution. And it's actually not a trouble for us. In general, it's probably, we're always going to have ones that do have unique solutions. But let's talk about what will guarantee that for us. So here is a theorem on the existence and uniqueness, and I'll talk about these because these words might not be necessarily clear. Uniqueness of solutions to, I don't know why that's all in parentheses, let's just put a little goal in there, to y prime equals f of xy, y at x naught equals y naught. Or if you want this in terms of x, it would look like this. We do these kind of problems all the time. So when can I be guaranteed that I have a single unique solution? So if, here's the conditions. Let me just make sure I get them here. If f, the thing that defines the derivative function, so if f and its first partial with respect to x, that's weird. Some of you might not have ever seen that. We'll talk about that. It's all good. I gotcha. Think derivative with respect to x. So WRT is with respect to x. That's a function of two, oh, excuse me, make this y. Sorry, I have my x version here and I'm translating it poorly. Derivative with respect to y are continuous in some rectangle R containing the initial condition. I'm kind of given a slightly less super technical version of this. Containing the initial point. Then we have a unique solution. Then there is, so first off, we know there's a solution. And we know that there's only one, and that's what the uniqueness is all about, unique. So this is existence, and this is, well, the word unique is there. I guess that's pretty self-explanatory. There is a unique solution in the rectangle. We don't know outside of it anything, but if we can just find one rectangle where this is true, then we're good to go. So let's go back to, let me let you get that up. I'm going to erase. Let's get back to our original problem over here. Take a look at it. See why it was befouled, or it was destined to be troublesome. So over here, come back to this. This is my f of y right here. So f of, and xy, I guess. Let's put that in. It doesn't depend on x, just depends on y. So this symbol here means first partial with respect to x. Let me put that here in case you've never seen that. That is the first partial derivative with respect to y. I keep saying x, I think. So here's our problem. Here's our initial condition. It's the point 0, 0. That's our initial point. I need for this thing to be continuous in itself. First off, this has to be continuous. So we need, let's write up what we need. Y to the 1/2 to be continuous in a rectangle containing, let's even, yeah, we'll just say that, to be continuous in some rectangle containing 0, 0. That can't happen because this function isn't even defined below the axis. So to be continuous, you need to be defined. That thing isn't defined below there. So right off the bat, that's a subtle matter. We can just say that's a problem. So note that y to the 1/2 isn't even defined for negative y. So in other words, down here, that doesn't make sense. So it'd be real hard to find a rectangle containing that point that didn't spill into the bottom. That's getting into some subtleties. But here's where you're gonna really see the problem manifest. But also, and I would even say more so, what is the partial of f with respect to y? Could somebody help me out here? How do I do that? What is that? You just derivative with respect to y. So you treat the y like a variable. If there was an x in there, treat it like a constant. What is the derivative of that with respect to y? Just wrote it like this. Katrina, what do you think?
I'm not sure I did some of this in like thermodynamics, but I'm having a hard time recalling it.
That's a
The
pretty
partial-
smart excuse to get out. That's a pretty good
No,
sounding
it looks
excuse.
familiar,
Yeah.
I'm just like trying to.
It's okay, thank you. So, I know a couple folks who can help me. I'm trying to get somebody else to help me here.
You just take the derivative of y to the
Yeah, that's it.
half of y to the negative half.
Thank you. Yeah, just power rule, right? You're probably thinking there's something heavier going on here, but this is just 1/2 y to the negative 1/2. So that is what this means. Just take that derivative. And I'm actually gonna write it in a fractional form because that's 1 over the square root of y. So we've got this. Notice that this isn't even defined at the initial condition. So this is not defined at 0, 0. That's a big problem. Not only are we not continuous at the initial condition, we're not even defined there. So we are not guaranteed a unique solution. And in fact, we've seen that that is the case. This whole unique solution stuff's about to become really important to us. And rarely will we actually check this theorem. It's not gonna be on exam 1 or anything like that, which is probably a week from next Monday, by the way. I think exam 1 will be a week from next Monday. I'll get you all the details on Monday and review stuff and all that. But I'm thinking that might be it. And if it's not, it'll be that Wednesday of that 2 weeks from today. Let me ask you about this. How about this one? Here's another problem. A couple here. We got y prime equals 4 plus y cubed. Y at 0 equals 1. Do we expect a unique solution? So you need to check a couple of things. This is f of y. You need to convince yourself that is continuous, and you need to find its derivative with respect to y, and convince yourself that is continuous in some rectangle around that point, and that point is this one right here. So see if we can just come up with some words or a loose argument. You don't have to do a continuity proof like in calculus with epsilons and deltas, for God's sakes. Because we know some basic facts, you know some basic functions. Done this stuff. So you could even answer a bigger question. Where are those two things continuous? Or where are they not continuous? What does it even mean to be continuous? That's a deeper question. We should probably talk about that. So William, what do I expect here? Do I expect a unique solution and y? Is this continuous? Why is it continuous? You're right, absolutely. Can you give me a reason? This might be harder.
It has no like breaks in the graph.
Yeah, nice. If you were to graph this out, this thing right here, f equaled that. I like that. So if I had f and y, this thing is just a cubic. Looks like that. It's a polynomial. So my reasoning is that is a polynomial. Polynomials are continuous everywhere. Think of every polynomial graph you've got. They're like this, or like this, or like this, but they're just wiggly lines, so there's no breaks. What about this one? Is this continuous? Yeah, everywhere, right? Because it's also a polynomial. So these are both polynomials, and that's the best of all worlds. Polynomials are continuous everywhere. And that's the kind of reasoning I would want here. So in particular, on any rectangle I could make around this thing, I expect a unique solution. So a unique solution, let's come back to our original after I get this done. Solution exists. Now finding that unique solution is going to be a little harder because what would we have to do? We would have to separate I don't know how to take that antiderivative on the left. That's like look up a formula or something. That's a beast to do that one. So even though we can't find a solution, we know that one exists and there's only one. So this is tough, but we know it's solvable. That doesn't necessarily mean we can do it with algebra or Diffie-Q techniques. But if we did a numerical solution, the one we get is the right solution. Let's come back to our original problem, which was this one. And let's say my initial condition is modified. So now change the initial condition. So here we have f is y to the 1/2. I have partial of f with respect to y is 1 over the square root of y. You need to draw a little picture to maybe see this, but I've got 0, 1, this is my initial condition. All I need to do is make sure that my rectangle doesn't extend below this axis, and I'm actually guaranteed of a unique solution in this rectangle because that initial condition gives me space below it to create a rectangle. So we can definitely find, we don't know how long the solution will exist or anything like that, but we can definitely find a unique solution to this problem. All right. I think we'll stop that. I think that's enough because I want to get into the fun stuff. There's a reason we're talking about multiple solutions. That is because it's leading into one of my favorite things to talk about. In fact, this was what my PhD thesis focused on. In a much crazier level, hopefully, right, than a day in DiffyQ. But we're going to spend a little while talking about bifurcations. Probably one of the coolest things in modern mathematics, and it's not even all that new, but relative to things in math, that's pretty freaking new. And especially with the advent of computers, this leads up to mathematical chaos, which we will absolutely talk about at some point, because that's freaking amazing. But we're just going to start off chill. So a bifurcation, let me tell you a little story here. This was actually the story that opened up my doctoral thesis. So I have a beam like this. So this is a semi-rigid beam. So it's made out of like plastic or something, but it's got a little flex to it. Got a little bit, but it's mostly pretty supportive and stiff. And it's resting on the ground, and it's anchored here. So there's an anchor. And there is a load being pressed down on it. So we'll say lambda equals a variable load. In other words, a weight being applied to the top of the beam. So here's the problem we have. We have this physical system, and let's do something fun, maybe. Maybe I can have some, yeah, hell yeah, multicolored fun. Semi-rigid beam, look at that. This is my equilibrium model, right? Like this is this one, unstable. And we've got kind of a similar thing here. So I've got a semi-rigid beam. I gotta make sure I don't like put anybody's eyes out with this. But I might need Tara to push on it really quick. So, but we'll see. So the load is my hand, and lambda is how much weight I'm pushing down on it. So if I keep pushing, notice it is maintaining its state. It is maintaining rigidity and holding that load up. But it's not a very stable situation. I don't know what's gonna happen here. And I have to make sure Cecil's okay, but you do have protective eyewear on, so I think it's okay. So I'm gonna press really hard, but any slight disturbance causes a buckling. So this is this is at equilibrium for most loads. And right, it was a certain load that made this thing become unstable. So if I just have a light load on it, I just push all day. It was when that load exceeded a certain value that things became dangerous. So what will happen is at some critical load, let's say at lambda equals lambda naught, the beam buckles. And it can buckle two different ways. It could buckle like this, or it could buckle like this. But it's a massive change of state. Once it buckles, though, it's actually pretty stable. It's not going to buckle again. It's not going to unbuckle. So what we had here is, and I'm going to start leading us into an idea. Here's lambda. This is my load that I'm compressing this with. And then here I have equilibrium state. So it starts off, I'm going to use dotted lines to be unstable. because at any moment it could buckle. But it can hold that for a while until some critical load is reached, at which point it buckles into one of two states, and these are stable equilibrium. There's two possibilities. This is called a bifurcation diagram, because it describes to us the equilibrium states and their nature and how they can change as this parameter lambda changes. And that's what we're going to talk about for a while. Parameterized systems that undergo changes of quality in their states. This is just so damn much fun. Let's start off with an example. Let's say I've got x dot equals lambda minus x squared. Lambda is a control node. So lambda is a parameter. It can take on, for this problem, any real number. So I'm going to be even more precise. Lambda is an element of, I haven't used that in here yet, but that just means is in the real numbers. If you've never seen that notation, that just means lambda is a real number. This is the element of symbol. And this is the symbol for the real numbers. And all I'm saying here is it could be any number you want, all good. The way to understand what's happening here is to think about all possible phase diagrams. So our goal is to understand all possible phase diagrams. And what I mean by that is where we take x dot versus x. And I'm just going to plot that thing like it's y equals lambda minus x squared. What would the shape of this be? What shape am I looking at here? Yes, yeah. Thermodynamics. In thermodynamics, we would learn that this shape could be, could be like that, right? Would this be lambda's positive, negative, zero? Which one is that? Negative. Shifted down below. So down here, this is the lambda less than zero. When lambda hits zero, what does this thing look like? Well, it's just this one right here. So there's the lambda equals zero. And then when lambda becomes positive, I see this break on through to the top half. But watch what happened, or just notice what happened. I guess it's not moving, so there's nothing to watch. When lambda is negative, there's no equilibrium. Because an equilibrium means that we've got x dot equals zero. So when lambda is less than zero, there are no equilibria. And just recall, we need x dot to equal zero for an equilibrium. We don't have that. As soon as lambda hits zero, instantly an equilibrium is born. So as lambda approaches zero from below, and when I say that, I literally mean in this picture, but I also mean from the left side, from the negative side of zero, the left side of zero. As lambda approaches zero from below, an equilibrium is born. At lambda equals zero. And you see it, it's just coming right there. So let's come take a look at this. Is that a stable or an unstable or neither? What is the nature of that equilibrium?
Unstable.
It's unstable. Yeah, and it's kind of one of those nodes, right? So it's half stable, because here I've got flow to the left, right? X dot is negative,
And over here I've got flows negative, so I'm actually gonna color that in to say solid on the right, open on the left, because it's unstable here and it's stable here.
But hey, we got an equilibrium all of a sudden. Just came into existence out of nothingness. And then we keep turning the knob, right? I've got this lambda knob. I've got this little dial that controls lambda. And here's 0, and we're turning it, and we just hit 0 with the lambda knob. And now we're gonna keep turning it to be positive. So as I turn it up to be positive, let's draw a new picture. You might want to make separate pictures for all of these possibilities. Here we have lambda is a positive number. So for example, I have something like x dot equals 1 minus x squared. Just to help if having the lambda around is stressful for you or a little confusing. And so I'm going to have 2 equilibria there. Where are those equilibria at for this thing here? So if I've got x dot and x dot equals this, where are those equilibria? What are the coordinates on those points?
The square root of lambda.
Thank you, Cormac. Yeah. So we have square root of lambda and negative square root of lambda. It's the solution to that equals 0. Yeah. Nice, thank you. So watch what happens as lambda gets bigger. As lambda increases, these move apart. So let's make some notes here, and then let's make a bifurcation diagram. Notice that as lambda increases, the equilibria move away from 0. And so I ask you now, we've got these equilibria, what is their nature? Are they stable, unstable? Could you please just take a moment and classify those equilibria? Arrows on there, right? I'll give you a second to do that. Does it make sense to everybody that we've got an unstable on the left and a stable on the right? We good? Happy to talk that through? Okay, cool. So a bifurcation, another diagram. You're welcome. This one looks a little different than the rest. We're gonna have lambda. There's someone lurking around. Hi. Oh, hi. Oh, hey. Okay, yeah, cool. You're welcome to stay. You're not gonna stay?
No, I'm in the lab right now, but.
Oh yeah, you got business. So I'm gonna put X star here, and this just denotes equilibrium. Notice here, I have the progression, and each slice of this thing is just one of those lines. So each of these vertical slices is one of those pictures for the corresponding value of lambda. So out here, there's nothing because this is where lambda is less than 0. There's no picture because the graph is below the x-axis. As lambda hits 0, suddenly an equilibrium is born. It is stable on the upper half, or the positive part, and unstable on the lower part, the negative part of the x-axis. So this just represents that x-axis, the phase line. And then this one moves away like this. In fact, it moves away exactly like that equation that Cormac gave us for the solutions. And there's another branch, and this one is unstable. So this one was stable. We're going to denote that with solid lines. This one was unstable. And we're going to denote that with dotted lines. This is x equals negative square root of lambda, x star. And we have a bifurcation diagram. Now I understand everything that can happen in this system. You tell me you've got some positive lambda. I know that there will be a stable equilibrium on the right and an unstable on the left. And I see how things are born. So this point right here is a bifurcation point because things changed. Bifurcation point right at lambda equals 0. There's a sudden change in the quality and nature of this system. Your turn. Got some fun ones here to look at. Oh yeah, there's a good one. So this kind of bifurcation, they all have names. This is called a saddle node bifurcation. They're ones that look like this. They either look like a parabola that way or a parabola that way. It's basically a sideways parabola. One of the branches is stable, one is unstable. It's sometimes also called, this one here is called a blue sky bifurcation, which is cool. So this was a blue sky bifurcation. Trouble came just out of the blue sky. Out of nothingness, all of a sudden somethingness. So it's a surprise. Let's take a look at a new one. You can please take a few minutes to find what you can find about this one. And I'll step in and give you some hints along the way. I think that's the one I wanted to give you. Yeah. So you might be like, oh my God, I've never done a parametric analysis. That sounds right. I would first just notice that this right side, it can be factored like that. So notice that this equation is actually this equation. And from this, when you set this equal to 0 and solve, you should be able to come up with some solutions. What you need to do is think about, let me give you the hints. So lambda less than 0, lambda equals 0, and lambda greater than 0. Take a few minutes. Enjoy digging into this. Ooh, it's very exciting, I know, but. Oh, you're all good. Give more hints. Make some pictures like this. X dot versus X. Just treat that like Y equals that. The Y is this part here. So if someone asked you to sketch this, you could do it. You've done it. You're here, M463. I know you've done that shit. You got it. But you probably haven't done it in such freedom on that lambda. Let me give one more hint to, not hint, but a helpful thing. If maybe just pick a specific value. You know, just set lambda equal to something in that range to get a feel for what it's like. That can make life a little easier, and then work from there. Tiny bites. This is going to turn out to be another important type of bifurcation. This is the kind that happens in a laser, actually, when it starts to laze. Is negative. This is what we want to see. We'll take a look at it in just a second. If that is still elusive to you, pick lambda equals 2, -1, lambda equals -2. Just take a look at what those look like. Let me do a parabola. I think the good old parabola might help. We have so many damn pictures floating around. X. Oh, hi. Wow, hi.
Sorry, I got kind of early.
You're really early. You're the second person who's just kind of come in here.
Just hang out.
I'll give you a few more minutes. I'll go through all of them because you're cranking this through. If nothing else, that lambda equals 0 case should feel
pretty good. 'Cause there's not much going on there.
Is that parabola shape making sense that I have on there? Anyone like me to talk through that parabola shape? I was like, more people coming in. It's Lou. I was already here. When you have a parabola like this, you want to plot it, just grab the zeros, x equals 0 and x equals lambda. So when I'm looking at the equilibria of this thing, it helps to factor it. Notice that x equals 0 is always in equilibrium no matter what lambda is. So no matter what lambda is here, where the hell is it? No matter what lambda is, I can always pull that x out and get x equals 0 as an equilibrium. So that's an equilibrium here, here, and here. But then I've got this other one. When lambda is negative, the parabola intersects over here in the left part of the x-axis. As lambda gets smaller in magnitude, closer to 0, this branch moves over this way. So you start to see this parabola kind of moving like this, and then it turns into that one. As lambda becomes positive, this is actually a double 0 right here. So when x equals 0, that's a 0 of multiplicity 2. Both zeros are crammed into the same place. But as lambda becomes positive, that second 0 starts to move away, and we see that picture over there. Now, I don't expect you to be good at this today, because there's actually a lot of moving parts and multiple graphs and ideas floating around, but I would like you to be good at it at some point, you know, in a week or so, something like that. We're gonna do lots of practice. Let's make a bifurcation diagram. So here are my equilibria. Here's my parameter. I'm going to put together these various pictures. So that one there, when lambda is negative, I'm in this part of the plane, I've got this 0 that is stable. So 0 is stable, and I'm going to mark that with a solid line. So right here, x equals 0 is stable. But then there's this other one, x equals lambda is another solution. And so it's literally x equals lambda is the other branch of this, and that is an unstable equilibrium. Look at the flow. I've got flow towards 0, flow away from this point over here, so I'm going to dot it. So this is x equals negative lambda. Oh, excuse me, no, x equals lambda. Oops. And that continues, well, we got this weird transition point
when lambda equals 0, I've got this little half stable thing here. As these two equilibria collide, they turn into this half stable thing. Notice it's still stable on the top where the stable part was, and then the unstable came to meet it underneath, and then it all changes. As lambda moves toward the right, that little 0 there, the lambda 0, starts to move away. And so we see that move away, but now it's stable. And the 0 is the unstable equilibrium. This is our bifurcation diagram. This is called a transcritical bifurcation. They have this X where you have, what we have here is an exchange of stability between two equilibria. There was two equilibria, and then they change their nature. So this is again a bifurcation point right here. We have a bifurcation at lambda equals 0. That's fancy. This is what a laser does, though. A laser, it wouldn't happen here at 0, but let's say you're pumping, pumping energy into a laser. Here's your energy. What you'll see is all of a sudden, at some critical quantity of energy coming into the system, it might start lasing, but it might not until a little bit more happens or there's some slight perturbation. So it might stay at a non-lasing state, but it could easily transition to a lasering state, and that's a stable state. It really wants to laser. It really wants to fly up to there. That's about all I know about lasers. And I don't know much. Has anybody here ever built a laser? It's like Dr. Gray or something. No? Has anybody wanted to build a laser? Like, come on. I mean, yeah. I spent a lot of time as a youth trying to build a laser. Spent a lot of time trying to do a lot of things. Let's go. All right, we got one more here. I want to give you this one, and I'm going to leave you with it, but I would like you to work on it right now. And then I'm going to give you a few problems. I don't have them right here. I'm going to post them on World Class. Could you please do this one? Come up with the bifurcation diagram for x dot equals lambda x plus x cubed. And then I would just toss in this little one. Also this one, which is very closely related, but not the same at all. Check those out. Please produce, with no karma, no grade or anything, please produce for me a bifurcation diagram. I would like to make a couple notes about top. They can each have an X factored out. So X equals 0 is always an equilibrium. Is equilibrium for all lambda. So you'll always have this line moving across here. You just don't, it might be stable or unstable, and that's the part you need to discern. So have fun with that, because that's actually pretty cool. And then I'll post actually some answers this weekend and give you a couple problems to work on. I honestly can't imagine this being on the exam, though. Like, this stuff takes thought and time. I'm not gonna put this on an exam. I'll probably give you a problem to do in your own time and have lots of no stress bifurcating. Maybe just take a few minutes to get rolling. Since we have 5 minutes. My God, what are you reading? It's a big book.